Thank you very much. I'm greatly honored to be invited by Professor Wong and Professor Bo Cheng Lai. This is my second visit to NYCU. Last time I visited in 2018. It was NCTU at the time. So it is great to be here. Great weather. And with regard to my talk, actually, first of all, I confess that I am not a good speaker. So you have to be with me and you have to raise questions. Otherwise, I become confused actually. Okay. So what I mean is that if you have any questions, concerns, some things, raise hand. Okay, simple question, good. If there are difficult questions, I'll refer to the paper because I will go through primarily the concepts and motivation actually. And that is what I have planned for, because there are a lot of materials actually. And this is outcome of last possibly 10 years of work that I have been doing. And more interesting thing for me is that these all research that I am going to discuss is organic. Organic means that we have evolved from one problem to another problem and so on. And I would like this as a takeaway outcome actually, because how we generated problems and how we moved defined problems, how we made it publishable, some inventive ideas and so on. That is all. Okay, so let me see. So what we have, so these I have divided into 7 modules. Basically, core modules are chapter 2, 3, 4, 5, and 7, and 7 is actually some other works. So what I have been doing is my work is quite broad. I do cross-layer optimization, and but in this discussion I am going to focus on the IoT aspects primarily, which is not necessarily new theory we are developing here, but we have utilized these learning tools. And basically these applied stochastics broadly, as we will see actually, and how we utilize these learning tools, simple learning tools and signal processing tools to get some interesting results, and which are, for me, this is very exciting because most of the things that we have done in this thing are actually implementable. We are trying to translate some of the things into real prototypes and to develop products also. So to start with, motivation of IoT is very well appreciated. I think all of you will appreciate this. Everywhere today we are talking about deploying these sensor nodes which will monitor the environment, and this will be remotely conveying the message for information gathering as well as remote actuation, remote control. Smart transportation, smart wearables, agriculture, smart agriculture, smart supply chain, smart home, smart manufacturing, smart city, smart grid. So I am going to pick up some of them, and as I will explain, actually, all these problems have been these IoT comes into the context from different inputs as I progress as a researcher last about 10 years actually. And even before getting into the IoT, what we have, for next few slides, what I will do is I will just give a very basic kind of primer of how I got motivated actually. So as we will see, some of the problems that we started with, I basically do applied stochastics, stochastic theory and optimization. So what that means is that I tend to view any dynamics of the system as a stochastic process, and I will so motivate that under certain conditions these are not holding well actually, and that is how I got motivated. But let us first go through how we used to approach our research actually. So measurement based or experimentation based, simulation based, and analytical. So what we tend to do in our lab, primarily try to remain in these two domains, two extremes, analysis and measurement, or rather analysis and experimentation. Some cases I used to rely more on simulation, but we are relying rather less on simulation, pure simulation. We are not leaving this is actually intermediate too. So, but they have their own trade-offs actually, as you can see. Measurement based in Indian context, for example, it's quite challenging because having these infrastructure is quite difficult sometimes. Instrumentation, experimental hardware required, and most accurate, it's replicable. You see why I emphasized on this measurement based analysis is because they are replicable. Analytical tool is universal language, right? If I prove some mathematics and anyone can just reproduce this, follow the mathematics and then reproduce the results. And likewise, measurement based, if I explain all the tool specifications, it can be replicated actually. Most accurate, but the challenge is that it's expensive and time consuming. Many times I do not give result for research that we need to have a timeline, time bound results, etc. Difficult. It is non-repetitive in the sense that I might explain that these are the tools I use, and then some researcher, some other part of the world possibly are looking at it, and then they find that they don't have the actual setup. Actually, it is rather quite difficult. So in that sense, to reproduce. And also, today I might have done some experiment, and then the system feature might have changed actually. So as a result, they also are, as the time evolves, this could constrain this measurement-based approach. And it is not compatible with future design. This is what I was talking about. Because, okay. Now, simulation-based on the other hand is we require simulator and programming skills, and it is high control over parameters. I can change the parameters, regenerate the results, compatible with the future system design, and so on. It is less accurate because I might have to now make some assumptions. This is one challenge, and it requires larger effort in the sense that I have to do encoding and so on. So less accurate. Again, feel free to ask questions. So this is intuitive, right? So, for example, if I talk about real life traffic simulation, how do I simulate real life traffic simulation? I have to possibly, let's say, consider this Poisson distribution or on-off process. But this is an approximation actually, and that is less accurate. And in fact, one of the modules, first module that we'll discuss is about that actually. And finally is analysis, system level understanding required, mathematical skills required. It is least effort sum in the sense that if I'm mathematically skilled, then I can manage, I can handle it, I can write the equations and so on. And high control over parameters. So system parameter changing, doing some numerical results are quite straightforward. Smooth compatibility with the future system design, same reason. But it is least accurate in the sense that some of the assumptions that are manageable in simulation may not be manageable in analysis. For example, I was talking about traffic arrival process as on-off process versus traffic arrival process as Poisson distributed arrival process. So Poisson distributed is more tractable, on-off process is much less tractable actually. But Poisson on-off process itself is also less accurate. And that also, how do I assume consider this on-off distribution also makes a difference actually. And some of the assumptions could be unrealistic. So when you do analysis, we have to be very careful. Professors are here, you will all appreciate actually. So certain assumptions have to make sense actually. So this is always a challenge. Now, as I mentioned, that our discussion is about stochastic process and where we fail. So the basic stochastic process definition, I believe all of you are aware actually. So stochastic process is stochastic process is a family of random variables xt, each defined on some sample space omega and function of time t. Basically, random variable which are function of time actually. So they could be discrete time process and with respect to the time. If I observe the system at every epoch could be, let's say, second, minute, etc. Or that is discrete time. And on the other hand, if I observe the system and there are some discrete states or continuous states, so accordingly I can have discrete state process or continuous state process actually. So for example, if we talk about this Markov process, continuous time Markov process, discrete time Markov process, and so on. Continuous state and discrete state, they're ways to think. Okay, so fine. Now this is very old. I am not going to go through actually. So this is how we deal with it. So one thing that we will, if I go back to the previous slide, is that what are the unique features? So please be with me. So I'll ask questions. Maybe try to respond to me actually. What are the unique features to deal with stochastic process? Meaning that if I have to characterize the stochastic process, what is the most interesting thing that I should have? Distribution, PDF, CDF, probability distribution function. Now, if I know the probability distribution function, that is the best thing I could ever imagine actually. Basically, I know everything about the system then. Okay, if I know probability distribution function, then I can generate any moment. That means I know everything about the process. But the problem is that we know that many a times we are not able to define the probability distribution function. Now, what is the next best thing that we could do? If we think of those who are researching on stochastic process, you will be appreciating that we primarily deal with first order moments and second order moment. Most of the cases, right? Mean variance. Okay. In fact, if you look at any Klein-Rock's results, first order moment, second order moment. What that means is that as long as we have knowledge about the first order moment and second order moment, we should be able to handle it. Now, what we do, if the first order moment and second order moment are not function of time, then we call this process as wide sense stationary, right? WSS process, right? So mean and autocorrelation function are independent of time, right? On the other hand, if going back, if I have knowledge about the distribution, and distribution does not change with time, that is called stationary process. So stationary process means this is called strict sense stationary process. If the process is strict sense stationary, then it should have a distribution, and if I know the distribution, I know everything. So strict sense stationarity. Now, as I mentioned, it is rather difficult to have any process in the real world to follow the strict sense stationarity, and also, as I mentioned, we do not require the strict sense stationarity for our characterization of system, because we primarily deal with the first order moment and second order moment. And our theory suggests that if we know the first mean, which is time invariant, and your autocorrelation function is time invariant, then we call the processes loosely stationary, which is called wide sense stationary. But the problem is that and then if I have such process which are wide sense stationary, they can be classified into so many things actually. This is a broad classification is semi-Markov process, and then within that there are classes. I am not going into the details unless you feel that this is to be discussed. Okay, I am going to skip through actually. So semi-Markov process, where the Pij, basically the system has multiple states. The Markov process has multiple states. Let's say I varies to 1 to infinity, 0 to infinity, and then the probabilities are known Pij, but they don't follow any distribution. They can be arbitrary. And f tau is the sojourn time in a state actually. So sojourn time in a state, this is also arbitrary. Then this process is called semi-Markov process. Within that you have classification called this is a subclass Markov process, where Pij, state transition probability, is arbitrary, but this f tau, the state time or sojourn time, is memoryless. or memoryless in continuous time, this is exponentially distributed, and in discrete time, this is geometrically distributed. So in that case, this is a subclass, actually basically restrictive. This is more tractable, but this is called Markov process. And then within that, another subclass is that if this Pij only certain transitions are allowed, rest of the transitions are not allowed, then this is called Bartlett process. Only neighboring transitions are allowed, and F tau remains memoryless, as that's why it is for the subclass. This is called Bartlett process. And then within that there is a class called Poisson process, where these if the neighboring transitions are allowed only, and then neighboring transitions are following the same what is that called? It is constant. Transition rate is constant, state independent. Then this is called Poisson process. And if there is no death, if there is no reverse transition going on, then this is correspondingly called a pure Barth process. This is like counting process, okay, renewal process. Renewal process is a pure Barth process actually. Of course, pure Barth process can be general. General renewal process can be general actually, and then there is a very specific cases called where this is lambda is equal to lambda. And then on the other hand, this is the random walk and the renewal process. That's why renewal process is actually overlap with this thing actually. Okay, so random walk is the Pij is Qj minus I, and this is very and the F tau is arbitrary, and then this renewal process is this. So in a sense, the renewal process, the Poisson process is a special class of renewal process. What is that? That is if the state time is memoryless, then this becomes Poisson process. If it is not, then it is renewal process. In fact, and those who are doing stochastic analysis, you will appreciate that dealing with generalized renewal process is actually also quite challenging. So we tend to, many times we actually get into this Poisson process assumption, exponential distribution of the state time, etc. These are the constraining assumptions that we make in terms of our analytical tractability. But more importantly, we are dealing with a system where implicitly assuming that the system has the wide sense stationarity. Right, so that is the problem actually, and that kind of motivates us to do something. So shortcoming of the stochastic process, stationarity of the process is assumed, which may not be true in real world, and mathematical models thus obtained is only approximate representation of the process. And what we deal with today, so these discussion that we are having today can be classified also in a better term called data-driven study. Actually, all that we are doing is that we figure out the nature of the data, and we figure out that these classical approaches of applied stochastics do not do well actually. So the data-driven optimization is what is possibly more interesting. So adaptive to the dynamics of the real world system, and it is robust, but it is computationally intensive actually. And that is actually a challenge, and today this is still interesting because we have a lot of computational intensive capabilities that we have, and also because we are now talking about edge computing. If it is computationally intensive, then I will possibly intelligently figure out where to get the computation done so that I can deal with it and deal with the dynamics of the system. So basically, we are dealing with the dynamical system, and that is what is the key motivation actually. Okay, so a couple of slides I just quickly go through. There are more AI experts like Bocheng. So basically the motivation for ML techniques in communication beyond classical communication. So this is actually for me this is quite interesting way to capture what we are doing actually. So in fact, you see, we have been doing these communications since possibly how many years? Since 70s we have mobile communication actually. Okay, and since 60s we have telephony and possibly Bell Labs. Professor Wong can give more history actually. So, but still, why we are still researching on these things? Because we are talking about more pervasiveness. we are talking about miniaturized devices, we are talking about these devices, we want to do everything with the device. We used to be happy with 1 minute call, just I'm alright or I'm not alright. Today we call possibly over hours, and simple phone call is not sufficient. We want to do video call and so on and so on. So that means that we not only are consuming more and more bandwidth, our requirement of quality of service, quality of experience has changed over the time, and also we want them to live longer. These devices should survive much long as so that we don't have to recharge frequently. So pervasiveness and also this is with respect to telephony, but there are other many applications where we are talking about this IoT. We want to do wireless monitoring everywhere. Network complexity, tackling growing heterogeneity of the and dynamics of the system. So these can be handled better using ML techniques. As I mentioned, these cannot be because of the complex network dynamics. We cannot actually characterize them easily using classical theory. So that is another motivation. And personalization is what I was talking about. Leveraging user behavior to enhance QoS and QE. Actually, so maybe I and you, one of you, might have the same telephony, mobile phone. But I might use it differently, you might use it differently. I might want it to last longer, you might want to have more quality information. So I might want to do same, let's say, communication. For example, I am watching cricket match. So I am just interested in barely seeing what is going on, and whereas other person is interested in properly watching, and then quality should be good, etc. So for the same device, for the same content that we are receiving, the content should be optimized for me differently and for the other person very differently. So personalization is very key, and that personalization also not only it is person dependent, but it is context dependent. When I am in office, I want to behave differently using the same device and for the same content that I am receiving. When I am on the move, I might want to do differently. So this is very interesting actually. So this actually changes with time, changes person to person, and so on. And also, if I have less energy available currently, then I will do something. If I have more energy, etc. If I have only a nearby charging point, I will do something. And need data-driven and ML strategies. So AI integration is enhancing signal processing, error correction, adaptive modulation, and wireless communication. So as we will see, some of the problems that we are dealing with are actually signal processing techniques, and we see that we can do better adaptive signal processing. ML algorithm employing neural network reinforcement learning for predictive maintenance and anomaly detection. These are some of the reasons. And resource optimization is for ensuring efficient utilization of limited spectrum. These are examples actually. So efficient utilization of limited spectrum and energy resources through intelligent algorithm, for example. Okay. So basically, these are the certain examples of why we need to have these data-driven and ML techniques. And as we go along, we will find more motivation why to map with these things that we are talking about. Now, why now is, I have already mentioned, beyond 5G, addressing critical need for intelligent solutions, the era of 5G and impending 6G, characterized by URLLC and MMTC. MMTC is massive machine type communication, and data explosion, which is also calling for newer solutions, managing and leveraging exponentially increased data. In fact, that is one of our motivations in 2 modules of my discussions actually. And innovation and efficiency. So harnessing AI to unlock new capabilities, achieve unprecedented level of network performance and efficiency. So this is okay. So again, this is just quickly go through the history. So AI/ML techniques. This basic AI technique is rather quite rich, has rich history. I think early 60s, this AI was discovered, but it went dormant until late 80s. And in 90s, AI/ML network management, and in early 2000, AI/ML wireless standards, and so on. So I'm not going to go through actually. So today we are somewhere here, and as I mentioned, so to me this discussion is exciting because I have actually not got into ML technique just because everyone is working on ML. So I motivate actually how we figured out that conventional techniques are not working well. Okay, that is most important thing actually. It is not because it is hot.